Yes. Okay. So since I'm registered, I'm going to start by complaint. Both in terms of one of the organizers and in terms of the Newton Institute, so this board is not appropriate for mathematical talk. So it's too small. It's easy, could be much bigger, and so this needs to be changed. So I managed to change the room, but one of the organizers told me that no.
So the main problem
no,
is that
that's fine.
they need
Everything was
a 90
arranged.
person on site there.
Everything was arranged. It was fine also for recording, and one of the organizers told me. So I'm complaining. That's all of my complaint now. Let's talk about mathematics.
Yeah.
So I think the organizing committee has to meet in an urgent session.
Okay. So I'm going to talk about the joint work of Uri Shapira, a joint work that I wrote here 3 weeks ago. It's brand new. I found a mistake yesterday. I corrected it tonight.
Last night.
Last night. So my English is not. I corrected it last night. So I hope it's okay now. Okay. So FQ is going to be a finite field of order Q, which is a power of some prime. R is going to be FQ of X, the ring of polynomial. In one variable, which I'm going to denote by y, by the way, over the field FQ. So K is going to be FQ upon this y, so the fraction field or field of rational fraction. And K hat is going to be FQ of double parenthesis y minus 1. It's going to be the field of formal Laurent series in one variable y minus 1 over the finite field F. So as a special request by Karen, I am going to give an analogy. So this is a non-Archimedean world, and I am going to give the analogy. So think.
Just a second. So Laurent series in y to the minus.
I'm going to define that. So R is going to be Z, K is going to be Q, and K hat is going to be R. So on this field, on the field K, we have an absolute value. So absolute value of K over Q, which is Q to the power degree of capital P minus degree of capital Q. And one way of defining the field of formal Laurent series is to say that the completion of K for this absolute value in the same way that R is a completion of Q for the standard absolute value Euclidean 1. So that does not define you an element.
Tell me what
Wait, be patient, you're quite aware. Okay? So I'm going to give a description of the element of this field. So the element in K hat may be written the following way, and that's the reason it's called formal Laurent series. So it's a sum over I bigger than some I naught, which is an element in Z, of elements of the form AI y minus I, and AI are elements in the finite field F. So formal series, Laurent series, because I'm allowing negative powers, and the variable is y minus 1 and not y, that's why it's this thing like that.
It's the computational place at infinity. That's what we do.
You and I know more words like that we don't want
No,
to plug in.
why is this the right analogy there? Why don't you take
So then, F in R, be patient in Padawan. Okay, that's can be written as a form, sum of I bigger than I not also element n of AI 10 to the power minus I, where AI is between 0 and 9. So, any such element, you can obviously regroup the negative powers of y minus 1 and the positive power of y minus 1. So it's written as a polynomial f, and so negative power in y minus 1 is positive power in y, just in case you're still sleeping in the morning. So this is an element of R plus an element which is power positive powers of y. So I'm going to define M, the set of f in K hat, where this I0 is at least 1. And this is an element M, and this is called the integral part. And this is called the fractional part. And well, we have exactly the same. Whenever the analogy is exactly the same as this one, I'm not going to write it. So that's okay with you, Karen? Karen approves, so I'm safe. Okay, so we have a map, capital Psi, from M minus 0 to M, well, the map, which element F associates the fractional part of 1 over F. It's called the RT map. And the same map, exactly the same map. So here M is the alpha point interval 0, 1, and the same map is called the Gauss map, but defined exactly in the same. So this nice map, these are the nice measure, so-called. It's not called because it's just multiple of the R measure. So you take the R measure of your locally compact field K hat and restrict it to M. And it turns out that this RT map does preserve this measure here. Okay? Here, Psi, the Gauss map preserves a smooth measure called the Gauss measure, which is 1 over 2. The Lebesgue measure of the field K hat, let's say R, restricted to M, 0, 1, but it's just an absolutely continuous measure with respect to the Lebesgue measure, and the factor is 1 over T. Okay, so now any element, say F to simplify, I'm going to restrict in an element in M which is not in K, or not in fraction K with M. So any such element can be written in the unique way, the form 1 over A1 plus 1 over A2 plus 1 over A3, etc. So where AI, that's the integral part of phi I minus 1 of F minus 1. And this is called the continuous fraction expansion. And this is defined exactly in the same way here. Yes.
So AI is a polynomial?
So AI now, what is it? It's an integral part of something, so it's a polynomial, and it's important that it's a non-constant polynomial. That's important for the convergence of discontinuous fraction to take place into this local. So same thing here. So the elements I'm going to particularly consider today are going to be the quadratic irrational. So let Qi be the set of quadratic irrational elements over K, which means simply that F is irrational, so is not an element in the small field, fraction field of K, and there exists A, B, C in K, and say A non-zero, so that AF squared plus BF plus C is equal to 0. Okay? So this is a quadratic polynomial. I forgot to say that characteristic is not 2. Otherwise, you have problems in this business. You can go around, but it's complicated. So this polynomial has another root, and the other root is denoted by F sigma. It's called the Galois conjugate of F, that's simply the other root of this quadratic polynomial. And in terms of the continued fraction expansion, everybody knows the analog in R, and this is equivalent to the continued fraction expansion of F is eventually periodic. That is, the coefficients AI after some time are periodic. Okay, so this is nice. So the orbit under the Artin map of psi is a finite orbit, and I'm mostly going to consider into the periodic part of the finite orbit because the first few terms might do whatever they are, but at a certain time, the orbit of the Artin map on my quadratic irrational becomes periodic. And so I'm going to denote by mu f 1 over nf, actually defined by nf, so eventually periodic. So I'm going to start to be periodic at the time rf, and I'm going to assume that the period length is n sub f. Okay? So I divide by the length of the period, and I put a Dirac mass at phi I of f, for I between Rf and Rf plus Nf minus 1, unless I'm making a mistake. So this is a very important probability measure on the periodic part of the orbit under the Artin map of this my quadratic element. Okay, so delta is the unit Dirac mass at the point which is indicated. Okay, and so the question is, well, so given a nice sequence Fm of quadratic irrational, what happens to the accumulation points of the measure mu Fm for the big star converge. Okay? So that's problem of a distribution of the Artin, the finite orbits under the Artin. Okay? I think it's a very nice arithmetic question. And so in the real world, there is a very nice theorem by Hecke and Shapira, which is only a particular case of a much general theorem. But take T a prime natural number in this case, and take f any quadratic irrational in R over Q, and what happens to the let's study these quadratic irrationals, P and F. What happens to them? Okay, so that's you always have difficulty mixing the additive and multiplicative theory in this theory of continued fraction expansion. So in this case, this measure simply mixture converges to the Gauss measure. Did I define it? So this is a very nice result. So these quadratic irrational distributes nicely towards a measure which is smooth with respect to the Lebesgue measure. So you're going to really have nice behavior. And so the main point of our result is that in the positive curvature, this is completely different. So everything is irregular. Okay, so it's no longer true. We are going to have problems with the behavior of the coefficients here. Their degrees are not going to be nicely distributed. Even the degrees of this polynomial here behave strangely, and these measures are indeed going to be in a very exotic behavior. Okay, so we can ask why? Why? Yes.
For this theorem, would you expect that any sequence of quadratic irrationals with kind of growing complexity would work?
No, because you can add exotic things. But if you these sequences are Hecke sequences of quadratic, and I'm going to define that. Okay, but no, you can have strangely a thing if you take quadratic at random. It's going, well, I mean you can construct things which convert to anything. Something just put your coefficients as you will here and. Okay, but I'm interested into nicely arithmetically constructed sequences of quadratic irrationals. Yeah, so things are going to be there. Yeah, so why? Why is this different? So you can think just a look at that. So what could happen to this kind of fix, right? Indeed, here we're going to fix P prime. In this case, simply means an irreducible polynomial over fq, and we fix the quadratic irrational. Okay, and we want to study p to the n. So, what is an obvious idea why things might go bad? Well, we're raising powers. Okay, and raising powers in positive characteristic has very strange behaviors due to the Frobenius automorphism. Okay? So the main point in this talk is, it's not going to appear here because I'm going to hide a lot of things under the carpet, but it's because of this Frobenius automorphism that things go bad. So here is a statement. So this is going to work with Uri Shapira, I told you. So as it was corrected last night, so there is a constant C, and such that for every number n, so look at the degrees of the coefficient ai of Pn. So what I'm going to write here is that these degrees behave very strangely. Okay? And in particular, there is going, in this sequence here, there is going to have a positive proportion of elements in this sequence, such that there is a maximum degree which is almost much bigger than all the other degrees. Okay? So I'm going to consider max over the period of these degrees divided by the sum of these degrees ai of in f when I varies over period of this element here. And this is really, most of the things is in one element. So if I subtract n, then the lim sup as n goes to plus infinity of this is at least c. This says that there exists one coefficient whose degree is much bigger than all the other. That's first statement. And so in terms of distribution of these measures, so these measures, so they are no longer going to converge. So this set of accumulation points might be very big. And there are any, and the accumulation points are no longer going to be absolutely continuous with respect to the nice R measure on K hat. Okay, so there are going to be singular measures even. Okay? I don't have enough room here because the board is too small. And I'm going to put a second. Statement on the board. Sorry, I have to erase the notation. If we had been in the other room, the notation would have been left on the board.
We got the message.
You got the message?
What is the English word for valeur?
What?
No, it's a joke, sorry.
Why concentrate on this kind of sequences?
Oh, I'm going to get to that. That's very natural sequences. They're called Hecke sequences, constructed in the Hecke trees, and there are nice sequences which go along rays in the Hecke trees associated to the prime. So nicely constructed arithmetic sequences. I'm going to get to that.
I forget, when you weighted when you put the direct measure down, did you weight it by the degree or?
No.
No, okay, it's
Yeah,
not
no.
related to the weighting.
It's another interesting measure to study, but that's really we want the equiprobability. Okay? It's going to be related to I'm going to say that again. Be patient on Padawan 2. I'm going to come to the reason why. It's homogeneous dynamics which is behind that, and that's the reason why.
And how does the period depend on n, the period of p to the n?
That grows. I don't know how it grows, but it grows.
It's a sum and not an average, right?
Yeah. That's very strong. Yeah, it kills everything. One degree kills everything. Okay. So, so there exist uncountably many sequences gamma n, n in PGL2 of R, so that for every f prime in Qi, for the other quadratic irrational, there is a constant C prime positive, so that if you look at the set of accumulation points of these equiprobabilities on Pn and then gamma n f. So the dot here is for the projective action of the element in PGL2 of R on the quadratic irrational. A, B, C, D act by A, F plus B divided by C, F plus D. So I look at these Q probability is here, and I take the star accumulation point, and I claim that there exists at least one accumulation point of this point, which is bigger than mu prime times the measure of f prime. So this is a measure which has support finite set. Okay, just the psi orbit of the periodic part of the psi orbit of f prime. Okay, so this measure is bigger than measure which has non-zero and finite support, so it's not absolutely continuous.
E prime is C prime, maybe?
We didn't see it. So it's a positive measure on finite set, so it's not absolutely continuous with respect to the R measure. Okay, so inside the accumulation sequences, you have lots of accumulation points which are not even absolutely continuous with respect to the R measure. Okay? So, what are the tools? So the main tool is dynamical one. So we're going to study the dynamics on the moduli space of R lattices in K hat times K hat, where I recall you that R lattices is rank 2, 3 R submodule of K hat times K hat, which generates K hat times K hat as a K hat vector space. So I'm going to consider them up to homothéties, that is multiplication by a non-zero scalar element. So on this set, you have the group PGL2 of K hat H hat, because it acts on the basis of K hat times K hat, and the stabilizer of your favorite R lattice. I mean, I don't know you, but mine is just R cross R. That's just PGL2 of R. And I'm going to denote by gamma this group PGL2 of R, by G the group PGL2 of K hat, and by X this moduli space here. So in the real world, where X is just PSL2 of R modulo PSL2 of Z, and this you know it very well, because this is a unit tangent bundle of the real hyperbolic plane divided by the modular group PSL2 of Z. Okay? So the identification between this moduli space here, I'm taking the quotient on the left because I want to take another quotient on the right. And so the map, and don't forget that the identification is by G maps to G minus 1 times pure standard lattice homothétic class of R times. Okay? So this is a space, this is dynamical space, and what is acting on that? So it's a diagonal subgroup. So I'm looking at the diagonal subgroup. Set of matrices of form star 0, 0 star in G, and don't forget that I've taken the quotient on the left by the lattice, and I'm acting on the right, by translation on the right, by the diagonal. Okay? So in the real world, everybody knows the matrices exponential t 0, 0, exponential minus t, or exponential minus t 0, 0, exponential t. Well, up to time reversal, okay? I don't care whether I'm going backward or forward. Never mind. So T noir And this acts on this exactly by the geodesic. Okay. So now, how do we relate these to quadratic and irrational? So here is a nice element, G sub f, constructed starting with my quadratic irrationals that I have fixed f. Consider the matrix f sigma f 1 1. So f sigma, remind you that's the Galois conjugate of f. Then I claim that this left coset under gamma, okay, this is an element in X, has a compact A orthogonal. I'm not going to prove that, but I'm going to convince you that this is true in the real, by picture in the real world. Karen proves again, yes. Okay, so, well, so you have the unit tangent bundle of H2R, so here is a picture of H2R. Now look at the geodesic line between F sigma and F. Okay. Well, but it's well known that when you project this geodesic line into the quotient modulo PSL2 of Z, that's a periodic orbit. Under the this geodesic line, the tangent vectors of the geodesic line project to a periodic orbit here, that is a compact orbit for the action on the right of A on this homogeneous space. And again, I like measures, and I'm going to denote by mu f the A invariant probability measure on the right orbit under A of this special element here.
Okay, but what does this space look like? Or maybe you're going to tell us.
Be patient, young Padawan. Okay, so here is a theorem which is due to Kemarski and the two present authors. We say that these measures again have a strange behavior. So here in this case, the real world, so a theorem again due to Hecke and Shapira, saying that the measures here, mu, I did not here, so mu, p, and f, defined exactly in the same way here, okay? With big star converge to the normalized UV measure on the quotient modulo by the modular group of the unit tangent bundle of H2. Okay, normalized to be a probability because this is a probability measure. Okay. So this is a nice result and not at all the case in positive characteristics. On the contrary.
So what is the geometric interpretation of this one? So it's like a distribution of closed orbits on the
Exactly. So you have lots of closed orbits. You have a family of closed orbits parameterized. Again, I'm going to that by long Hecke tree, and if you take your arithmetic defined sequence, this sequence of periodic geodesic equidistributed. But you can have sequences of periodic geodesic which is not equidistributed at all.
But this has something to do with the fact that some Hecke operator associated dilation by a certain amount becomes dense or something.
Yeah, it's a bit more involved than that, but there are things like that you need to pass to S arithmetic, to work in S arithmetic world. I mean, that's what these guys are doing. Indeed, okay. I'm going to talk about this.
Is there any hope of estimating the speed at which the convergence is
Yeah. There are much more precise.
what I meant.
They have very precise speed of convergence uniform. Yeah, they are up to the Riemann hypothesis, because sometimes when you work in this kind of thing, Riemann hypothesis occur very soon. Okay, so up to things like that, they have a very precise error estimate. Okay, and here we don't have at all an error estimate because we don't have convergence. So here we are converging to a probability measure, but that's not the case in general. Okay? So theorem, there exists a positive constant C, the same as here above, or almost. No, not the same, almost. So that for every theta, which is a weak star accumulation point, of my sequence of measures mu, p, and f, actually the total mass of this measure is at most 1 minus c. Okay? So you have a loss of mass, you have at least a c loss of mass whenever you take any weak star limit. Okay? So it's not even converging to a probability. Okay? So we have more stronger result than that, but just what I wanted to state for now. Wait. Question? Don't hesitate to ask questions.
I'm sorry,
Yes.
I mean, my functional analysis is poor, but nonetheless, that seems like I'm just confused. I thought that the
Space is not compact.
I thought the space
Modular
was
space
a
X.
probable
It's not compact.
X is not compact.
Yeah.
Ah, and therefore the space of probability measures are also not compact. Thank
I answered the question
you. Yes.
correctly.
So, yeah, that's right. So there we learned something about letters.
Yeah, X is not compact, right? Both in the standard case here, and I'm going to draw more pictures. Okay. So that's the basic tool, but that now you need a tool to relate this tool to the problem. So tool to apply. Okay, so it's going to be the Bruhat-Tits tree. So let O, the set of elements in K hat, which have no negative powers of y minus 1. So I naught is at least 0. Okay, so that's the formal power series in y minus 1. I'm going to denote by T, and I'm going to define it, the Bruhat-Tits tree. On my group, PGL2. Okay. And before I define it, the analog here, you know it. It's the real hyperbolic plane, which is PSL2 of R, modulo on the right. That's why I want to take the quotients on the left by the lattice, modulo PSO of 2. Okay. So it's a tree has vertices. And the vertices are going to be the all lattices in K hat times K hat. So O is a ring. Again, up to scalar multiplication by non-zero elements of K hat. And again, since group G acts transitively on the basis E, it acts transitively on the set of all lattices. So there exists a transitive action of G on this set, at least, of vertices. So what are the edges? So sorry for all of the sorry. So the edges, well, there is one edge that I like. So the favorite, I mean, I don't know yours, but mine, my favorite O lattice is just the product O lattice. And I'm going to put an edge between this lattice and the lattice where I multiply the second vector by that. So I have one edge here, and now all the other edges are going to be constructed by the action of G. They move two vertices to some two other vertices, you put an edge there. Okay? And so the stabilizer of your favorite lattice, this is PGL2 of O, hence the set of vertices of your P is a quotient PGL2 of K hat modulo PGL2 of O, and again, not the analogy here. Okay? So this is a maximal compact subgroup of this group in the same way as PSO2 is a maximal compact subgroup in PSL2 of. So this tree is a Q plus 1 regular tree with a space at infinity, a projective line of K hat, which I obviously identify with K hat union infinity. Okay? So, analogy, I've already made the picture. Do it again. H to R, at infinity, you have R and 1 point at infinity. Okay, so in the tree, it's going to be the same. Not enough room. I already did that, so. In this board, I'm going to draw a very flat. Okay, so I'm going to put infinity here, not very far infinity, but okay, and then I'm going to draw K hat here. So again, I have this standard lattice O times O, and I'm going to move by an edge to another lattice O times YO, and it's Q plus 1 regular. Okay, so there is one edge which goes towards infinity, and all the other edges will go backwards. And make picture like that. Okay, so sorry if it's flat. Okay, and then we have this. Okay, so how do you understand the number of edges which goes out from every port? Okay, well, you need to so you have at least one edge here, and the other one, but you have the stabilizer of point which is acting here, and the only thing which is important here is what happens when you take the quotient modulo m, so O mod m. Okay, so in fact the link for every vertex of the tree, the link B is a projective line over the finite field FQ, which I identified with FQ union infinity. Okay, and I'm going to label the edges precisely by FQ union infinity. So you have one edge infinity which goes up, and then you have the edge 0, 1, something, 2, in FQ. Okay, and again, if you when you iterate, you have the edge infinity from here, which is the inverse of this edge, 0, 1, 2, etc., etc. Okay, so we have a labeling of these edges, and considers the geodesic ray. Okay, so it's not going to look very geodesic, which converges to a point, to my point F. Okay, and the subset of K hat, which are the endpoints of the geodesic rays which start by 0, is exactly, I need another color, this set here is exactly N. Okay, so the set of developments which have only positive powers of y minus 1 are the set of endpoints of the geodesic rays here. And how do you recover the labels AI in the Laurent series expansion? Well, you have 0, A1, A2, A3. These are just the labels of these edges. Okay? Yeah, AIs are not the coefficients of the continued function expansion. They are the coefficients of the Laurent series. I should not have used the same letter to do them. So,
Okay, wait, they're numbers?
they are polynomial.
Oh, they're on.
Okay, they are. No, the AIs are FQ. Yeah.
They're numbers. Yeah,
So
yeah, yeah.
the continued fraction expansion
Otherwise
coefficients
it'd be
are
too much
polynomial.
information.
But the AIs
They're numbers.
of the development in the Laurent series, they are elements in FQ, in the finite, including 0. Okay, so I'm going to work a little bit more on my lattice, which is called Nagao lattice, except maybe from some Gaulois irreductible, we might call them Veil's modular group, but Nagao considered it before Veil. So this is a lattice in my group G. It's very important to understand the quotient of my T by my lattice. The quotient has an appropriate category, so the orbifold category, that is the quotient graph of groups. So as a graph of groups, it's a ray of groups. And it has stabilizers. Stabilizer, the first one is PGL2 of the finite field FQ. And if you are at distance R, then you just consider an upper triangular subgroup consisting of matrix AB0, B, where A and B are invertible elements of the finite field. And the degree of the polynomial, so these are polynomials, right? So is at most n. So now everybody knows the analog in the real case. Since this is the orbifold quotient of H to R by PSL2 of Z, and this orbifold quotient behaves like that. So you have two singular points with groups Z over 2Z and Z over 3Z. And then you have a thin cusp which goes all the way to infinity. So up to quasi-isometry, the sets are the same. And we like working up to quasi-isometry. Everybody agrees on this scope.
Is that the only geometric group theory in the talk?
More is going to come. Okay, so the analogy is even more striking because look at the order of these groups. How do they increase? So that's the number of polynomial of degree n, of a finite field. So the degrees here have exponential growth. And that's exactly the fact that these here, the small horospheres here, are exponentially small. Okay? That's exactly the same fit. Okay. So I had a red line here. So what happens to my red line when I project it with my red? What happens to my red line when I project it? So it's going to start by this. Okay? And what can he do? Well, he can go up to some point. Then what does he do? Well, he has to go back. He has some time. But when you go back, what do you have to do? Since this group are strictly increasing, you have to go back all the way to here, to the origin. And then you go up. At some time you decide to go back. And you have to go back all the way down.
Wait, why? Wait. Can you put the indices in the...
Because the group here are included. You have a strict inclusion here, right?
Which one?
This one is contained in this one. The group are increasing.
Okay, well...
So are
You would be
are you describing the image of some other path?
I'm describing the image of this
in
path.
this particular fundamental domain or something.
It's not a fundamental domain, it's a
Well,
quotient. Okay?
quotient.
So I have a tree here and I have a quotient map. As a graph, it's just a quotient graph. So I'm
I see,
pushing.
you're just,
This is a quotient graph
yeah,
as a graph. So I'm drawing the thing as a
you're
graph.
just pushing, yeah.
Yeah, I'm explaining that. I'm going to get back more. But it's just because you cannot, if you wanted to go back, it means that you would have an element in the stabilizer here, which will not stabilize this point.
Okay, so every indices are... What are the indices?
Oh, you want the edginess group?
Exactly. Just the numbers.
It's 1 Q, 1
Ah,
Q,
it's
1
okay,
Q,
that's
1
what
Q. Yeah,
Okay.
Q.
So every edge stabilizer is equal to the vertex stabilizer on the
Exactly.
left, except for the square.
Yes. Except at the origin, where at the origin, you are allowed to go back, okay? And so you go up, and you go back, and you go up, and I'm going to stop there. And the first guy who saw that is actually Serge. It's interesting. Okay. So, from dynamical point of view, it's important to look at the space of geodesic lines. In T, and you have an action of the geodesic flow, the discrete geodesic flow, and you just push by time n at the source. And this is the group PGL2 of K hat acts transitively on set of geodesic line. The stabilizer of your favorite line is an action with A with PGL2 of O. And here again, you have acting on the right the element 1, 0, 0, y to the power n. And instead, acting on the right, this is fine because A is commutative, so you can still act on the right here. And this is an equivariant map. And this is the reason why one of the tools relating the dynamics of A over here and the dynamics of the geodesic flow here. So let me now give a geometric interpretation of the continuous fraction expansion, which goes back a long way, long time ago. So, okay, so I'm going to define H infinity as being the orbital in centered at infinity, such that the standard lattice O times O belongs to the boundary of H infinity. And I'm going to denote by, I'm going to consider the family of orbitals, gamma H infinity, where gamma varies into my lattice gamma, of course, modulo the stabilizer of the point infinity, which also is the stabilizer of the orbital. So this is a nice family of orbitals. I'm not going to give you the analogy, but I'm just going to send you back to Caroline series work, which is completely beautiful and explain very nice ways the relationship between continued fraction expansion and the geodesic flow on the modular curve.
So since we're at attribution, that's actually due to Arti in the paper of 1924.
Yeah. The first thing, but the nice way how you relate the Gauss measure with respect to the UV measure and things like that. I know it's an expository paper. You can refer to beautiful paper even in the expository. Okay, so again, sorry for the very flat
So can I
picture.
just ask a stupid question? You say geometric interpretation of what?
Of this family of robots and
No.
the continued fraction expansion.
I think you've written
Continued
CFE.
function
Expansion.
expansion.
There we go. Good. Thank you very much. Okay.
Sorry.
There we go. Yeah, great. Okay.
Okay, so you have this overall center at infinity, which is called H infinity. Okay, and it goes through your standard base. And then this family of ball, in fact, actually cover. So this is a picture of T. Okay, rather a model, the ball model of T, and ball model a bit flattened because of the.
You don't have enough space, right?
Thank you. Thank you. So you have one ball which is centered at 0, for instance, and then you have another ball, etc. at some point, and again another ball, and I'm going to stop for some time. And look at my geodesic line. What is my red color? Here. So my geodesic line starting from infinity and ending at the point F. Okay? So this family of ball covers the tree. So I have to enter into one of the ball and then exit one of the ball, then enter another one, and then exit it, and enter another one, and then exit it, etc. All the way to infinity, and since I am irrational, I'm never going to converge to a point E. Okay, so
What does a horrible look like in the tree?
horrible.
Is it just a ray? Or
No. So it's a subtree which has only
one end.
one end. Exactly. Look at in the tree that I have drawn and erased.
I remember.
Take an horizontal line and take what is
Oh, I need everything in that height. Okay.
Yeah, same picture as in the Republic plane. Okay. Okay, so I have this, and what's very nice that these points here are the partial quotients of the continued fraction expansion. That is when you truncate your continued fraction expansion at time n, you get the fraction, and that the points at infinity of the n for n plus 1 ball into which you enter. And furthermore, so you have to enter in your ball and then leave, so the distance you travel is even. It's a fact. In a tree, normal in tree. And what is this distance? That's just the degrees of the coefficients. Here, degree of Lm of F. Okay. So that's a very nice picture, and this allows me to state the last proposition. So we really this picture. That's where we understand. This is also a way to consider these zigzags. Okay. So your group acts transitively on the boundary on the horospheres, and each of these zigzags is an excursion into a cusp. Okay? So if you think in a modular curve, you have excursion into the cusp, and you go back rather down, okay, you're not going to have geodesic which stays, they have to go back. Okay, so it's same thing. So the main technical tool, and I'm going to end with that, there is a nice cross-section, C max, cross-section for the action or the diagonal group A on my modular space X, so meeting, so every orbit, well, I'm cheating a little bit here, in a countable set, and a beautiful map theta from C to the space M of that I have defined, so is that if T from C to C is the first return map, which is well defined because you're only eating the A is a continuous group in some sense, so totally is a continuous group, but not uncountable group. It's eating this sectional at a discrete set of times in some sense. And here's the first return map. Then we have a beautiful commutative diagram. So first return map goes from C to C, and then you have a map from M to M, or almost really well defined map from M to M, which is Artin map. And your theta here is going to make this diagram commutative. And if you disintegrate your measure f with respect to this cross section, and you push it forwards. You push forward this homogeneous measure on the A orbit, disintegrating with respect to this cross section. What you get is exactly the equidistribution on your finite orbit on the periodic part of the finite orbit of the Artin. And that's the end of that.
So geometrically, the one high degree is causing this thing to go way, way up into a
Absolutely.
and that's causing some of the mass to exit out the.
That's
Yeah.
exactly. Okay, that's why you have a loss of mass. Okay, you can go back. That's why the two are related. So you go high, you lose mass.
This phenomenon of excursions already arises in the classical
I know.
case, where there is no loss of
No
mass.
loss of mass.
So what? So how about this?
Frobenius. You have a strange thing which happens because of this Frobenius automorphism. It's too long to explain.
You can't say it has something to do with the difference between the geometry of the hyperbolic plane and the geometry of this symmetry.
The geometry is very close. You know?
Yeah, I agree, they're very close, right.
You have a modular ray and you have a modular curve.
Somehow
The geometry is very close.
Yeah, I agree. But I'm just wondering whether there's
The
a fine
arithmetic,
distinction.
it's the arithmetic which is defined. Okay, so it's the same defined arithmetic, so I have no time to talk about Hecke trees. Same kind of arithmetic which produces very different behavior.
Yeah. So, if you have F, can you relate the compact A orbit?
It's a compact A orbit, yes.
So it has a measure.
Absolutely. Or an ET measure, yes. That's
Now,
mu
but
F.
I mean, when you normalize the measure on A, it gives you a number. I mean,
How do you want to normalize it? I mean, you can.
you normalize the Haar measure on A, and then you have a compact orbit
Yes.
that has a measure. So
Yeah,
like the period of F. So
It's
can you
related.
relate it to
It's
F?
related to. Yeah, it's related. That's if you normalize. So A has a maximal compact subgroup, which is the intersection with PG2 of O. Okay. Normalize this R measure. So this gives a 1. Okay. And the mass is exactly the length of the planet curve.
Okay. Because there is another way, there is a rather subtle theorem of U, that if you you know, if you take the periodic orbits, in this case, if you take them all together the same length, of finite length, and now this equidistributes.
That's
Is
the
there
point.
something?
That's very different because it still equidistributes in positive curvature. So the spheres of the Hecke tree, so we proved that that's one of the arguments in the previous paper with Kemarski. We proved that the Hecke spheres still equidistribute. But it's just even if the Hecke spheres still distribute, these no longer distribute. That's the point. Thank you. I'm going to erase the
I have one more question.
Yeah.